Hello and welcome to this video about establishing versus using continuity. Now there's something very subtle about the definition of continuity, and these two different tasks are sort of opposite of each other, so we'll talk about this in this short video. So what is continuity? Well, looking at page 118 of the 7th edition of Stewart's Calculus, if you just paraphrase this just a little bit, it says that a function f is continuous at the x value a if this equality right here holds. Now this equality doesn't have to hold in general, so saying that a function is continuous at a specific x value actually means something. There's a long version of this because there's a lot that's implicit in this definition, and Stewart admits that as well. So this left side could exist or not, meaning you could have a number or not, and this right side could exist or not, and so that could be a number or not. And so what's meant by this equality is really that both of these things are numbers first, and then that this equality happens. So that turns into this, right? The left side exists here, the right side, this f of a exists, and these things are equal. And what it means for the limit to exist, for the two-sided limit to exist, it means that the two one-sided limits exist, the left and right limit exist, and both of those numbers are equal. What it means for f of a to exist, just said slightly differently, is that a is in the domain of the function f. Alright, so that's the definition. There it is again, and the whole point of this video is that when you consider this particular phrase, f is continuous at x is equal to a, and that's another way to say this, there's sort of two types of tasks that exist, which are in a sense the opposite of each other. So the first is establishing continuity. That's when you're tasked with, here's a function f, and here's an x value called a, and you have to show that the function is continuous, which means you should actually go through these steps and show, answer the question, does the limit of f as x approaches a, does that exist? You got to answer yes to that. You got to show that this is true here, that f of a exists, and you finally have to show that those two numbers are equal. That's what establishing continuity is about. There's sort of this opposite task, which is using continuity. So if you can from some other sort of source get that a certain function f is continuous. So if you just have this fact with you that f is a continuous function, then you can do something with it. And one of those things you can do is actually just go back to the definition, and now you're not trying to show that this equality happens. Now that this equality is true, you're going to take advantage of the fact that this equation is true. So that's kind of the idea of what using continuity is about. And continuity is used for a number of other things, like this thing called the intermediate value theorem, which we won't talk about in this video. But what I want to do is kind of go over both of these ideas more, give an example of how to establish continuity, and then I have 3 examples of using continuity at the very end of this video. So establishing continuity, you got to answer yes to all 3 of these questions, and these 3 yes or no questions, you have to answer all yes to get f is continuous, and if you answer no to any one of these questions, then f is not continuous. And look, this all works with the long version of the definition of continuity, because all of these 3 things have to be true, which would mean you'd have to answer yes to all of these questions. So let's actually go through this process for sine of x at this x value pi over 2. Sometimes this text here, the x value, that's cut out, so you'll see something like show sine of x is continuous at pi over 2. So in the context of this problem, a is equal to pi over 2. There's the graph of sine of x, and let's cover this thing with a ribbon, with a vertical ribbon, an orange ribbon at pi over 2. And you have to guess what the y value is. That's what limit is, after all. That's the intuitive idea of limit anyway, is as you approach this way towards the ribbon, you'd guess that the y value there is 1. So we have a limit of 1. Okay, we're done with the ribbon. Now we actually, part 2, needed to show that f of a exists, or in this case f of pi over 2. And sine of pi over 2, yeah, now we actually need to uncover the ribbon. Definitely, we get a particular y value here, and that is 1. And these two numbers, 1 and 1, match. And therefore we've met all 3 requirements to show that sine of x is continuous at pi over 2. So that's establishing continuity. That's kind of going through this flow chart once. And on page 1, 2, 3, there's this thing called Theorem 7, and it says this. There's 2 requirements. If, first of all, f is one of these types of functions, so if f is a polynomial, or maybe f is a rational function, or maybe f is, sine, cosine, tangent, cosecant, secant, or cotangent, or it's an inverse trig function, or it's an exponential function, or maybe f is a logarithmic function. As long as f is one of these types of functions, so that's the first requirement. And the second is that you're looking at a number a, which is in the domain of the function f. So as long as both of those 2 requirements are satisfied, then you can just conclude using this Theorem 7 that f is continuous. So how does this work? We didn't prove this in class. The book doesn't really prove this either, and I mean, the proof of something like this is kind of difficult. We actually just went through what happens for one trig function just now, namely sine, at one particular value in the domain. But really the point is, for each of those functions on that list that we just saw, and for each a value which is in the domain, somebody went through this particular flowchart, in a sense, or gave an argument that you could go through this flowchart, and that you'd always get yes, 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 and so that the function would be continuous. So that's really, if I go back this slide, this is somebody establishing continuity for all these different types of functions. And now, if you know that a bunch of different functions are continuous, you can actually use this fact. So intermediate value theorem is one case. We're not going to actually do that here. But another context where you can use continuity is, well, this sort of simple one that goes back to the definition. So suppose that you had to compute the limit of a function as x approaches a. That's what you were tasked to do. And maybe your function f is on that list in Theorem 7. And you know that a is in the domain of f. Then you're in luck, because the task is going to be very short. Just remind you what the definition of continuity is, at least the short version. It said that this thing here, this limit, the thing you were just asked to find, is actually the same thing as f of a. So instead of computing this limit, instead of doing all this calculus, you get to do this algebra. You just get to evaluate a function at one particular value. So that's really nice, right? So this is a big time saver. If you have a continuous function, limit of f can just be replaced with f of a. So let's give this a try. Here's this example, first of three, limit of 2 to the x as x approaches 4. And here's how you can do this. So 2 to the x is an exponential function. It's a is equal to 4. 4 is in the domain of this function f. You can plug that in. In Theorem 7, these two conditions are met. So 2 to the x is continuous at 4. That means continuity means this is true. And if you just plug in the function 2 to the x for the f, and you plug in for a, you plug in 4 everywhere, then this just turns into this statement right here. And what is f of 4? That just means, oops, sorry about that. That just means 2 to the 4, and that's just 16. Okay, second example, same idea. So logarithm is a continuous function, and 1000 is in the domain of that function. So both requirements of Theorem 7 are met, and so therefore this function log of x is continuous at the x value of 1000. And that means, well, continuity, what that means is that this equation is true. So we should, now that we know this function is true, now that we know this function is continuous, we can just use this fact. That means plugging in a is 1000 and that f is log. This thing which we were asked to compute can just be replaced with f of 1000. And f of 1000 just means log of 1000, and this is log base 10. So 10 to the what power is 1000, and that's 3. Last example is this one. Limit of tangent of x as x approaches pi over 2. Now tangent of x is a trigonometric function, so that's good. First requirement is met for Theorem 7, but the problem is that pi over 2 is not in the domain. So we can't use Theorem 7 because the second requirement hasn't been satisfied. If you actually compute the left and right limit separately by doing some graphing, you'll get that the two limits are infinite and they're different, and therefore the limit of tangent of x does not exist. I mean, it doesn't exist anyway because of this infinity business, but this limit is not positive infinity or even negative infinity. It just truly doesn't exist because the left and right limits don't even agree. Okay, so that's it for the examples, and really just to provide one slide of context, the direct substitution property is only to be used for polynomial rational functions, and what the DSP really is it's just using continuity. It's just saying, well, look, you have this Theorem 7 business, which says that polynomial and rational functions, among other functions, happen to be continuous. And because they're continuous, you can just replace this limit problem with just evaluating the function. So that's what the DSP really is. It's just sort of continuity, but just for a basic sort of collection of functions, just to get you started computing some limits. But really, the story behind DSP is that polynomials and rational functions are continuous. And then finally, just as a comment, for functions which are not polynomials or rational, but which are on that approved list in Theorem 7, then Theorem 7 combined with the definition of continuity gives us something that works the same way that DSP actually does.